In this video, we consider the following problem. A charged particle, electron or proton, moves into a region of uniform magnetic field B, goes through half a circle, and then exits that region. It spends 200 nanoseconds in the region. We should answer the following three questions. A. Is particle electron or proton? What is the magnitude of B? And if the particle is sent back through the magnetic field along the same initial path, but with 3 times its previous kinetic energy, how much time does it spend in the field during this trip? Let's start with the case A. Is particle electron or proton? Because we have only 2 options, we can use method of trial and error. So we assume first that the particle is proton and find magnetic force on this particle when it enters the magnetic field B. Actually, we need only direction of magnetic force. To do this, we introduce the 3-dimensional coordinate system, which is shown here. Z-axis is normal to the plane of the screen, so it is parallel to magnetic field, and we can represent magnetic field with this vector. The velocity of the particle is in negative y direction, and for positively charged particle, which is the proton, we can find direction of magnetic force using the right-hand rule. So applying the right-hand rule to these vectors, v and b, we can find that magnetic force points in direction to the center of the semicircle. It means that this force is a centripetal force for this motion, and our choice of nature of the particle is correct. Particle is a proton. And now we consider the second part, so we will find magnitude of magnetic field B. To do this, we assume that semicircle has a radius r and calculate the time which particle needs to go through this path. This time can be found by this equation, where p times r is the length of the semicircle, and v is the speed of the particle along this path. We don't know this speed, but we don't need it. For a radius of the circle, we have the following equation, which is given in the textbook, and we use this equation to replace r here with this r. As a result, we have the following formula for time which particle spends in magnetic field. You see, we need to know mass of the proton, which is given, charge of the proton, which is also given in the book, and magnetic field B, or vice versa. If we know T, we can find B. B is given by this equation. Now we know mass of proton, charge of the proton, time which it spends in this region. Plugging in all this stuff in this equation, we get the final answer. B equals 0.164 Tesla. Part B is solved. The last part of the problem has very simple solution. Increase in kinetic energy means that the speed of the particle when it enters the region of magnetic field also increases. But if we look to the equation for the time t which a particle spends in the magnetic field, we see that this time doesn't depend on speed of the particle, v. And for this reason it remains the same. So the answer is that even with increased kinetic energy with increased speed, particle spends exactly 200 nanoseconds in the region of magnetic field. So the problem is solved completely.